Welcome back, everyone. We are going to be working on measures of variation, meaning how different are each of the data to one another. We're going to start with the range. The range of a set of data values is the difference between the maximum data and the minimum data value. For example, here's a list of data that I used in a different video. And we're going to take the maximum data, which in this case is 26, and I'm going to subtract the smallest data, which in this case is 22. So what's the range with this set of data? It's just 4. Let's do the same for the next example here. So we have this list of data, 16, 26, 12, 9, 17, 26, 11, and 14. The largest data there, it looks to me, is 26. Again, just happens to be the same as the one above. 26. And let me preface, this is the range. 26 minus the smallest piece of data, that's looking like 9 to me. So 26 minus 9, we have a range of 17. Now, we don't use the range all that much. It's worth mentioning, I guess, but the big way that we measure variation in data, meaning how different is each data from one another. And that is what we call the standard deviation. The standard deviation of a set of sample values is denoted by a capital S. Is a measure of how much data values deviate away from the mean. The formula is here. Where the x in this, let's start with the square root. And then inside that, we have that sigma again. That's a Greek letter capital S. And it stands for sum, meaning we're going to add up all these little pieces here. The x by itself that you see in the formula means each data point is going to be subtracted by the mean of the data and then squared. And all of that's going to be divided by n minus 1, pardon me. The good news is we are going to be using, instead of this formula, we are going to be using one var stat. So that's stat calculate, and then one var stats. And what we're looking for is S with an X next to it. That's going to be our sample standard deviation. Let's talk about standard deviation a little bit. Standard deviation is a measure of how much values deviate away from the mean. The average, right? The value of the standard deviation, S, is always positive. The units of the standard deviation are the same as the units of the original data values. What that means is if I'm collecting data and I'm measuring it in inches, when we calculate the standard deviation, it is also in inches. And the sample standard deviation S is what's called a biased estimator. Of the population standard deviation, meaning it's biased based on the data that we've collected from a sample, which of course is not the population. So we just need to keep in mind that we know that the sample standard deviation is going to be different than was likely going to be different from the population standard deviation. Now, these two lists are the same list that I used in the previous video. I put this into list 1 and this one into list 2. And we're going to find the standard deviation of this data. Let me show you real quick. There's my list 1 and my list 2. And I'm going to run one var stats on both of those to get sample standard deviation. We'll start with the first one. I'm going to go to stat, calculate at top, one variable statistics, one var stats, and I'm going to run that on list 1. SX is my sample standard deviation, so that's 1.67332. And for my second list here, I'm going to go to stat, calculate one var stats, and I'm going to go to list 2, second 2. My standard deviation there is 1.642. So pretty easy. It's really nice. We don't have to use that crazy formula. Some teachers still do use that, which is fine. All right. So here's one from ALEKS. They give us this list of numbers, and I want to show you that I actually have those numbers in list 3. You can see right there in list 3, 36, 43, and so on. So I'm going to run one var stats. One var stats to get my standard deviation. Stat, calculate one var stats on list 3. So this is my list 3. Second 3. And there's my standard deviation, the SX. That's the 6.1237. 1237. All right. Not too bad. All right. So now we're to the range rule of thumb for identifying significant values. To find a rough estimate of minimal and maximal usual values. Now, I want to really emphasize this. When I say usual, that typically means we're within 95%, meaning those outer 5% are what we call unusual readings. So for example, let's say that we were in a room of people and the average height was 5'4", and we look around and we see someone who's 6'8". Well, that's unusually tall. It's not that the person is unusual, it's just relative to everyone else's height, that's an unusually tall person in that group. And here's how we determine what is and is not usual. So the minimum usual value is going to be, take the mean, and we're going to subtract 2 standard deviations from it. If it's more than 2 standard deviations away from the mean, then it's considered unusually small. The max usual is going to be the mean plus 2 standard deviations. Now, later in the semester, we'll learn why it's 2 standard deviations, and that captures about 95% of the data. But these ones we're definitely going to keep an eye on, especially as we move on to our next example. So we have a batch of chocolate chip cookies. With the mean number of chips, there's our X bar. It's 24 chips. And the standard deviation, that's our S, is 2.6 chips. Use the range rule of thumb to find the minimum and maximum usual number of chips, then determine whether 30 chips are unusual. All right, we're going to use our formula above there. So for the minimum for usual is going to be X bar minus 2 standard deviations. So in this case, 24 minus 2 times 2.6. So 24 minus 2 times 2.6. So that's about 19 chips. And the maximum for usual is going to be X bar plus 2 standard deviations. Four plus 2 times 2.6. That's about 29 chips. All right, so let's make sure we understand what we mean by this. So let's say I randomly select one of these chocolate chips and I count the number of chips that are on them. And there are exactly 22 chips on my chocolate chip cookie. Is that an unusual number of chips for that chocolate chip cookie? No, that's between 19 and 29 chips. So 24 chips would not be unusual. I'm going to select another random one. On this one, there are 20 chips. Is that unusual? No. We're still between 19 and 29. However, if I randomly selected a chocolate chip cookie from this batch and there were 14 chips on it, that would be considered unusually low because that's below our 19 chips. So when they ask whether 30 chips are unusual, we would say that 30 chips is above 29, so this is unusually high. So this is what we mean by the range rule of thumb. The range rule of thumb for identify significant values. All right, let's move on. Here's another range rule of thumb. This is for estimating the standard deviation. And so the standard deviation this is an approximation. If we only have limited information, then we're going to take the range, which if you remember, that's the maximum minus the minimum, and divide it by 4. Now, where does that 4 come from? I'll show you in a minute or two where that 4 comes from. So let's quickly use the range rule of thumb to estimate the standard deviation in a sample with a minimum of 19 and a maximum of 30. So S, our standard deviation, is an approximation, is going to be 30 minus 19 divided by 4. 30 minus 19 divided by 4. So standard deviation is about 2.75. So again, we try not, if we have the data, we're not going to use this. We would use the data instead. A couple of notation. So if we have a sample standard deviation, that is going to be, and we've been using it for this entire video, a capital S. And the sample variance is the same S, but squared. So if we have the standard deviation to find the variance, we just square whatever that number is. The population standard deviation is a Greek letter, lowercase sigma. It's a circle with sort of a tail coming off the head. And once again, the variance is the square of that, so that's going to be sigma squared. And I know this Greek letter stuff can be a little confusing, so we have an example here from ALEKS that is going to help us to distinguish what is the sample and what is the population. So here we go. At the beginning of last summer, climate scientists issued a report on the thickness of the ice shelves of Antarctica. The report states that the population mean was 765 meters with a population variance of 12,100 meters. Now, this one is talking about, in this case, to be very clear, that they are talking about the population, which means if we're talking population, then we are talking that the mean in this case is going to be the mu, and the variance is going to be sigma squared. Because you can see population variance right above there is there. And we talked about mu earlier as being the population mean. After reading the report, Jessica wanted to verify these results. She examined at random a random sample of 25 of the ice shelves and found that the sample mean, so this we are now at, this is X bar, and a sample variance, that's S squared, 11,025 square meters. So let's try to get the right characters down as we're looking at this. The population mean is 765 meters. So the population mean is going to use, when you choose the options there, it'll be mu. The population variance, and we can look up above there, the population variance is going to be sigma squared. The sample variance is going to be S squared. So I know it can be a little overwhelming. I do get it, but yeah, it's not too bad. And that brings us to the empirical rule for data with a bell-shaped distribution. Before we move on, let's talk about the diagram here real quick. You can see the mean is right there in the middle, the X bar, kind of a purple on the graph. And each of the bars to the left of that is one standard deviation away. And what we're talking about here is we're looking at the area under the blue curve. So the kind of lighter blue that's underneath it is the area. And one standard deviation away, so that's X bar minus S, X bar plus S. If I add all that area together, that gets us about 65% of all of the data is within there. We will learn where these numbers are coming from in a different chapter. If we go 2 standard deviations out, that means we're going to capture about 95% of the information. Now, if you remember in the range rule of thumb for standard deviation, it was the range divided by 4. Here is the 4 that we are talking about. So if we go 2 standard deviations out, you can see we have 1, 2, 3, and 4. That's where those come from. So, and if we go 3 standard deviations out, we're capturing 99.7% of the data. Usually we're just interested in 2 standard deviations away. Anything more than that is going to be unusually small or unusually large. All right, and if we go back to people's height in a room, if the average is 5'4", then you can see most people are going to be within 2 standard deviations away. About 95% of the people are going to be within those heights there. But then there's going to be some people that are unusually small and unusually tall. And when I say that, I'm not talking about the people are unusual. I'm saying relative to the data that we have, it's outside of that 95% range. So let's apply this. Example, in a nationwide test taken by high school students, the mean score was 48 and the standard deviation was 13. The scores were normally distributed. Complete the following statements. Approximately 99.7% of the students scored between. Okay, so let's go back to here. 99.7 means that we are 3 standard deviations away. So how do we figure this out? Here's my X bar. Whoa. This is my X bar. X bar. And here is my S, my standard deviation. So we're going to go 3 standard deviations out. Again, we know that because 99.7 means that we're going 3 standard deviations away. So here we go. 48 minus 3 times 13. 48 minus 3 times 13. So this is going to go from 9. And then we go 49 plus 3 times 13. I typed in the wrong number. 49. It should be 48. So it was right originally. This is 48. 48 plus. So 48 plus 2 times standard deviation, which is 13. So 74. I apologize. 48 plus 3 times the standard deviation, not 2, 13. 87. This is going to be 87. And we can see for part B So now we're looking for a percent of the students scored between 22 and 74. So I'm going to do this. I'm going to draw. We're going to have right in the middle here, our 48. And I'm going to go up and down a couple of standard deviations. And I know out here, we're at the 9 and the 87. So I'm going to go 48 plus minus 13, 48 minus 13. So this is 35. 48 plus 13. It's going to be 61. That's one standard deviation out. This is one standard deviation away. So this is a standard deviation here, and a standard deviation here. And if I go one more out, so if I go 48 minus 2 times 13, I get 22. And if I go 48 plus 2 times 13, I get 74. Once again, each of these are a standard deviation away from the mean. So now we're going to look here between 22, and we can see we're right there. So 22 is here, and 74, which is here. And this is 2 standard deviations away. So 1, 2, 1, 2. And if we're 2 standard deviations away, what percent of the information is between there? 2 standard deviations away is going to give us our 95%. So what percent is between 22 and 74? That is going to be 95%. All right. Last problem of the video. The links of movie files that are available for streaming are modeled using a normal distribution shown below. The mean of the distribution, that is our X bar. X bar. And the standard deviation, that's our S, is 20.2 minutes. In the figure, V is the number along the x-axis and is under the highest part of the curve. U and W are numbers along the axis that are each the same distance away from V. And they are referring to these letters here. Use the empirical rule to show to choose the best value for the percentage of the area under the curve that is shaded, and we need to find the values of U, V, and W. Well, let's start with the easy one. The easy one, V, is the mean. This is 189.7. And what I'm going to do to figure out what W is I'm going to keep adding a standard deviation until I get a number between 220 and 240. So let's do this. So I'm going to take 189.7, and I'm going to add a standard deviation to that, plus 20.2. And I'm looking at W on the graph there, and 209 is below 220. So I need to add another standard deviation. So plus 20.2. There. I am now in between 220 and 240. So this is 230.1. I'm now going to look at U. I'm going to take 189.7. Now, I did say that they are equal distance away from V, so it's most likely going to be 2 standard deviations away again. And I want to be really clear on that. That means that this distance here is 2 standard deviations. So I'm 189.7, I'm going to subtract the 20.2. And 169.5 is not between 140 and 160. So I'm going to subtract one more standard deviation. That number does get me between 240 and 140 and 160. This is 149. 149.3. And once again, that was exactly two standard deviations away from the mean. So if we are two standard deviations away from the mean, what does our empirical rule tell us? Two standard deviations means that we have 95% of the data. So the answer here is 95%. Not too bad. I hope that helped.